plastic drain tubing, plying it in with the corrugated wall plastic drain tubing with a laser beam depth and grade control. That's the whole concept of the research project that we'll be discussing and illustrating. This was developed through USDA ARS Pioneer Research. They call it Pioneer Research. We were the only ones doing it and the first ones to do it and was stationed at the Ohio State University. The team for this was myself, James L. Faust, and my research technician, engineering technician, Norman Fozzie. This is later in our career, myself and Norm Fozzie. We considered ourselves research partners in this project throughout. It ranged from about 1960 to 1974 where we worked together on the project. My major advisor at Ohio State was Dr. Glenn Schwab. I worked for Dr. Schwab as an undergraduate student for 2 years before I got my engineering degree in agricultural engineering. And he became my major professor in my graduate programs of master's and PhD there. We became very, very close colleagues after completing my degree and continuing research. A very important mentor early in my career was Professor Virgil Overholt at Ohio State University. Dr. Schwab came to Ohio State and replaced Mr. Overholt when he retired. Virgil Overholt is the grandfather, if you will, of the International Drainage Hall of Fame. It was named after him. The Overholt Drainage School, it's taught there at OSU. He was always inspiration to me. He always told me when I got started on the plastic project, he said, "You young fellas don't know that this is probably not going to work out. But since you don't know that, you young fellows have a way of making things work, and if it doesn't work, you abandon it and find something that does." And it was kind of an inspiration. He really followed my early career very closely. Let's do some history on the early research of plastic pipes for subsurface drainage. Much of it, almost all of it, was centered around the use of the mold drainage plow to put in drains, using the mold plow. The technique that Dr. Schwab used in a PhD program at Iowa State in the early 1950s was to pull in a smooth wall plastic tubing into the mold drain channel from the outlet. This was not his operation, but this was a plow that I had, and put some pipe in like that to demonstrate the process that he used of the pulling it in. Now you were limited to how far you could pull it because 100 feet, 200 feet was about the maximum length before there would be enough drag on the pipe you could break the pipe and trying to pull more pipe in. The problem with the smooth wall pipe is it didn't coil up, and this was a picture Dr. Schwab had given to me as to one of the reasons why the idea never took off at all, because it was a very cumbersome material to handle. If you made a pipe, say 3 inches in diameter, it wouldn't coil. Soon after that project at Iowa State, in the mid 1950s, in the later 1950s, ARS started a research project at Cornell University to put plastic liners inside the mold drain channel. And what they developed over there, and I've got them all lined up here, was basically the arch liner to keep the roof of mold channel from collapsing. I later, when I had to take over the project, put a bottom in that to see if it would improve the hydraulics, but it did not improve the structural aspects of the liner. Caterpillar Tractor was a cooperator on that project, and they used a wider sheet of plastic. This is all vinyl plastic, PVC. What they call the overlap. This picture, we put some tape on it to hold it together. This thing coiled together, and the smaller pipe in the soil they put a cap over it, an arch over it. They called it the overlap with cap. My assignment on this project, when I was assigned the project right out of engineering school, uh, meeting with about 6 people that had worked with these types of liners for about 2 to 4 years and discussed all the problems and so forth. I was assigned to make a closed circle, lock it together. The instructions were they didn't care whether I taped it, glued it, stapled it, or whatever, but it had to be a closed circle. And I developed, along with Norm Fawsey, what we called the zippered plastic mold liner. It was interlocking tabs along both sides of the 10-inch wide sheet, uh, and zipped together as it was put in the ground. And I'll show you the machine to do that. This was kind of an efficient looking operation, since this roll of pipe that made 600 foot of drain, and it weighed 60 pounds, so it was a pretty efficient material aspect. And the cost of the material, this was 15 mil thickness plastic, was not that excessive. They, it, it generated some interest using plastic for drainage. Uh, this was a zippered pipe that liner that I developed. Uh, Dow Chemical had a styrofoam plastic. They said, well, we could use it for a liner. This was used basically for insulation and heating ducts and so forth. They invited me to the Dow plant in Michigan to see this operation and extrusion, and they thought it could be extruded underground. When I seen the machine, I told them, I said, well, it's a pretty neat operation, except that you can't start and stop this thing. Once you get going, you just have to keep working right through lunch and shut it down at the end of the day. And well, we put drains in, start and stop, and they hadn't even thought of that. So the whole idea was just an idea, and that was about it. This is the mold plow that we had. It was got from the earlier projects, and the liner is put in through a shank, hollow shank, that's pulled behind the mold plow blade. And our first project on this thing, after developing the zippered pipe, was in Crookston, Minnesota, and also a companion project in Fargo, North Dakota. This was really just a few months after I started in January 1960, and after Norm and I were satisfied that the thing would zip pipe together as we put it in the mold drain. In some trials at Ohio State University, we were told to go to Minnesota to do it. I wasn't really ready to do that because we had just got started, but was instructed by the administration in Washington that if we didn't get it done, the ground would freeze up there and they'd lose another whole year and not have the experiment in the field. So we went ahead and did that. This is the way the zippered pipe was put in through that hollow blade. It's folded, fed, and round the corner, and zipped together with a zippering die inside the machine, and brought out as a circular zip together. I'll show some pictures later about it. So totally depth and grade on it was a challenge from the beginning. This is on this mold plow. These wheels were not for depth control, but they were just to make it a trailer when you got it out of the ground. In the early trials, I used a stretch string it was parallel to the grade we wanted, and lay the pipe, lay the liner, and used 2 guides on it. I was watching this and manually controlled that. We tried to keep the machine in a neighborhood of less than 100 feet a minute ground travel, give me some chance to control that. Proved not to be very successful. This is another picture of it. For cold weather operations, and we were working in northern Ohio after we got back from Minnesota in late 1960. We put a canopy around that and some heat lamps in that to keep that sheet of plastic warm, so we could put it in during colder weather. Otherwise, that sheet plastic get pretty stiff in the cold weather, and it could possibly even crack. Uh, we also had a project to put in at Purdue University. These projects at Minnesota, North Dakota, and Indiana, and actually one down in Utah, were promised before I ever got involved in the project. And the original researcher at Cornell University resigned from ARS and took a job in Australia, and that's why the job opened up. And Dr. Schwab recommended that the project be moved to Ohio State, and he recommended me for the job, so that's how I got started in it. But we took the whole operation. This was our government tractor trailer that we operated. We drove it ourselves, hauled it to Walkerton, Indiana. This was muck land, muck soil, and installed an experiment there. The last experiment that was promised earlier was out in Logan, Utah, and we loaded all the equipment on a Hertz truck. Couldn't find a government-owned truck that was suitable for this trip, and hauled it all the way to Utah. We mounted the plow on a D8 Caterpillar tractor that the Utah State University provided, and we installed the plastic line mold range in a field that had been pre-graded. So we used the depth wheels on this mold plow. This is a plow we actually built ourselves. It was on a toolbar and not the trailer like one you saw in the earlier pictures. And we used, basically, we put zippered pipe in and also some overlap type pipe in this experiment. I was back, this was an interesting site because the drainage in this one was for salinity control. And it was artesian pressure from the mountains here brought water to the surface and brought salt with it. And so all the drainage water coming out of these drain pipes was not from rainfall, but coming from artesian pressure underneath. I was back to this site 20 years after we put this project in. This was done in 1963. I was back there in 1973, and those drains were still flowing, and somebody had mentioned they had never stopped flowing in all that time. I'd been away from home for quite a while, and when I got back, I took my wife and the kids, and they could see what I was doing, being away on a long trip. The kids had to check out the zippered plastic liner and how it worked. This is the floating beam plow that Norm and I put together. It had hitch points along the side with hydraulic control, and the wheels could be used for depth control, or if you put them in float motion, the plow operated what we call a floating beam plow. This is a pendulum device. I'll talk about it a little bit later. But the traction for this thing, we had a D4 to help pull. This was an old D7 tractor that did not have enough power for really heavy clay soil. This was the plow out of the ground, showing the linkage between the liner, feeder, and the plow blade, the mold plow blade. And this is just the lift to hold it up. The wheels are not used for transport in this case. This is a close-in view of the zippered liner coming out of the tool. And this device was to put some soil back over top of the liner so there wouldn't be soil falling from down through the slit. And so we literally tried to mold the soil back around this tubing. It was a narrow slit. It wasn't a trench at all. And this is a closer view of how that compacted soil back over the top, so that it was, instead of backfilling as much, it really molded that zippered liner right into the mold channel. We could put this tubing in at 150 feet a minute, It really works pretty slick, but and I really said at the end of it was the idea just didn't work out. It turns out that the pipe wasn't really strong enough over the long term, and we had instruments, and I'll show those, of measuring the diameter. We had experimental drains that were 400 feet long, and every 100 feet we had a access barrel down to them. We could pull instruments in and out and gauge the diameter. But this is the zippered liner, the overlap with the cap, and the plain overlap. This was maintained the diameter better. This was probably 9 months after it was installed for all these, and the overlaps and the overlap with the cap was deteriorating pretty quickly in diameter. And this was 9 months. The gauge was what we call a strain gauge mouse. This is out 4 years, and we used different size wooden plugs, 2-inch, 1.5, and 2-inch, pulled through it from those 100-foot sections from either section. And this is the percentage of the drain length that we could pull those plugs through. And you can see even the zippered liner after 2 years was really pretty bad. It didn't take much of a deflection in the sidewall for a 2-inch plug to get stuck. The drain tube was 3 inches in diameter. This is the instrumentation. This was in today's technology. This was all analog instrumentation, no digital or anything. The strain gauge mouse had 6 fingers on it with strain gauges on it. We recorded. It gave us a diameter. These are the wooden plugs. It makes a pretty simple operation. Either goes or doesn't go. And this was a grading device. It indicated the number of lights would indicate the slope that this plug was pulled as we pulled it through the drain. We had a pulley operation with, we had wire and cable through every mold liner. We put that in as we installed the pipe, and we pulled those plugs through and pulled the mouse through, pulled the grate from every 100-foot barrel. This is a 50-gallon barrel that was buried into, and the pipe came into that. Pretty intensive operation. We had the V-notch weirs and FW1 recorders to record the drainage flow out of all of these. Very intensive project to evaluate the thing. The 3-inch diameter zipper drain, well, that was the installed shape. After about 2 years, it took this shape. This was an argument Dr. Schwab and I had. He always felt it would flatten, and I always said no. The soil at the top has not been recompacted to the degree of the soil at the sides, and so it would point up, which was exactly what happened. And after 4 years, the soil started collapsing around the side, so it became a deteriorated shape. And I decided pretty early in the game, even way before 2 years, that it wasn't going to be strong enough. Dr. Schwab had reminded me at young in my career that what I thought probably didn't count for a whole lot, but I needed to have the data to prove that it wasn't strong enough and wouldn't work before I would talk about it in a paper. And so it was a while before I had enough data to really prove for sure that it was not going to work. The early methods of depth and grade control and the high-speed drain plow equipment that were evaluated in testing the different types of plastic bowl drain liners. These methods have proved to be slow, costly, and not accurate enough. Thus, the search continued for a good method. As I said before, the stretched grade string or wire for depth and grade control and visual reference. And it was a challenge for the operator to actually control that with these kite pointers or even more precise pointers at the round speeds possible. You couldn't pull this thing at 25 feet a minute. Those tractors in those days, to pull that draft on that plow, had to open up the throttle. So it had to be at least 75, 80 feet a minute, and we typically could install the pipe, zip the pipe together at 150 feet a minute. Stretch string reference, and I even walked alongside with a control box in my hand to get closer control of the pointers on that string, and it still was a challenge. We I had an early thought of using the laser beam type control for this, but laser beams weren't available yet, and we needed to work on the hydraulics. So I had mounted on the plow a fluid dampened pendulum, the kind of pendulum that's used on side hill combines to keep the threshing components level. I blocked the sideways movement and used the movement of the pendulum forward and backward only, and electronic switches that operated the hydraulics. It basically did a fairly decent job, but it was always on the right slope, but not necessarily the right depth. And we also used this pendulum device on a trenching machine, and it worked better. In fact, the vibrations on the trenching machine even improved its performance. It wasn't that bad at all. But the bottom line on this was it really helped us figure out how the hydraulics should respond for grade control on a drainage plow. How fast it needs to be, how sensitive it needs to be. And so while we were waiting to find some kind of a laser beam or light source for grade control that didn't have an off machine, had an off machine reference instead of an on machine reference. And I called this an on machine reference. Then we solved it. This was an idea that came from England. I met Dr. Ansley Eade from the United Kingdom. He was a researcher there. He also developed a zipper liner for a mold drain, and it was amazing that we both came pretty close to the same type of zipper pipe, except he zipped his on top and bottom because he couldn't figure out how to do it with just one zipper on the top. And he was amazed that I was able to fold it up and zip it on top, and not crease the pipe on the bottom. So, but he had a radio-controlled depth and grade control. He put a rod, a survey rod on the back of his plow, and he would set his level up on grade line, and would watch that and radio control it. And I told him, I said, was that plow is that so many, like 200, 250 feet away, it's going to be hard to see that, even with a telescope. And he said, oh yeah, but we English have great eyes. So we had a good laugh out of that. But this never panned out as an operational process. In the mid-1960s, our project was getting enough attention. They started increasing it. Norm and I have been working on the project, but Ron Reeve came from Riverside, California, the Salinity Lab, to be the research leader for all drainage and irrigation research in what we called the North area, the Corn Belt area states, about 8 states. Lyman Willardson was the scientist that we put this project in at Logan, Utah in 1963. He wanted to come to Ohio State and work on his PhD under Dr. Schwab. And he also wanted to stick with us on our project. This was our secretary and one of our engineering students that worked for us. We always had several engineering students. And I think this was the day, the reason Norm was all dressed up, I think this was the day he completed his bachelor's degree in soil physics, agronomy department. We arranged, I had completed my engineering degree before I started with ARS, and Norm, I hired him. He was working part-time and then going to school part-time, and I arranged with him to work with me for a whole year to get the project going, and then we allowed him to go to school part-time to finish his degree, and this was what was done. I think this was about 1964. So really a good day. The drainage materials and equipment R&D. It really, after 1965, when we basically said the plastic lime mold drain wasn't going to work out, discovered and got samples of the corrugated wall polyethylene tubing, drain tubing. We made it a drain tubing. The floating beam type drainage plow instead of a trencher to install the corrugated tubing, and the laser beam automatic feedback depth and grade control system. That became the three phases of the project that we basically launched in 1965. And that is what the three stories are about on the Transforming Drainage website, and it's written up and digitized and are available to view or download from there. This webinar illustrates those stories. This was the sample of the pipe we first got from a company called Havoc Industries over in Delaware. It was small diameter, 2 1/4 inch diameter. It was used originally in the United States for underground electrical conduit. They put it in new subdivisions, housing subdivisions, and when they were ready for telephone cable, electrical cable and stuff, they would pull the wire into these and wire it into the house. The machinery for this, the corrugation machinery, was developed in Germany about 1961. And its first, as I said, its first use in the U.S. was for underground electrical conduit. But no one had used it for a drain pipe in the U.S. Germans used it for a drain pipe. It was made of PVC, but it was very small diameter. 2 and 3 inch was big enough for them to be a main. The height, we basically, at that point, when we were seeing this kind of flexibility and strength, the high-speed installation of subsurface drains using plow-type equipment became possible and practical in the mid-1960s with the development of the lightweight, coilable, corrugated wall, high-density polyethylene plastic tubing, pipe wall openings made for saltwater entry. When we got this tube, we ran it through a saw to put some holes in it so we could use it for a drain and for experimental purposes. We modified the pipe feeder. We just made a hollow blade to feed the pipe in behind the mow plow blade, and recognized pretty quick when you could put this pipe in 150 feet a minute. We needed to have a satisfactory and efficient way of controlling depth and grade on this high-speed plow. It was essential to make the plow method of drain installation practical and acceptable. This was all during what we call the space age. We even, at Ohio State, they were experimenting with 3 satellite dishes instead of one of those monster dishes, and seeing if the signals from satellites could be interpreted as well as small satellites as the big dishes. We said this was all during the space age. We even had the thought that, boy, it'd be nice if we could control the depth and grade on this plow from the satellites, the GPS type technology. And we remember joking about it and said, well, we can probably be on in the right county in the right state, but not necessarily the right field, and to put drains in us. And the elevation resolution on satellite technology at that stage in the 1960s was not good at all. But our installation speed that we found in trials with this was 90 to 150 feet a minute. It was pretty common. The initial field trials we used for this was at Coshocton, Ohio, in 1965. We did it at Coshocton, which was the hydrologic research station east of Ohio State University by several miles. We did it at a place that was not really accessible to press. We didn't want a lot of people around when we were trying this thing out. We put drains in a side hill seep area that was giving them trouble. We did allow there 30-member staff to come out to observe the operation after we got going. And so it was a pretty successful thing. We were very, very happy with how it worked. These early coils of that pipe were really cumbersome to handle, the way they handled, the way they shipped them and so forth. And we realized that was something we'd have to work on if we'd ever going to perfect this method. Several months after that initial field trial installation of corrugated tube, that the ASCE, the American Society of Ag Engineers, sponsored the first National Drainage Conference held at Chicago, Illinois in December 1965. At that drainage conference, I presented a paper, Plastic Drains and Their Installation. The paper was published in the conference proceedings, Drainage for Efficient Crop Production. It was actually January 1966, but the conference was in December 65. That the highlights in that paper was that it basically said the plastic line mold drain tank concept was terminated because it just didn't function. And the preliminary field test results for the corrugated wall plastic drain pipe plowed in with a modified mold plow attachment. We were satisfied with that and really reported on that. And the need for an automatic depth and grade control system on the drain plow to make the high-speed plow and method of drain installation accurate and acceptable. It was just something that was essential. The planned use of a helium neon gas laser beam was described for an off-plow grade reference line with a laser receiver unit mounted on the plow draft beam or blade. That was an idea presented there. I think the attendees were a little skeptical, maybe quite skeptical of that idea, especially since the laser beam had only been invented about 3.5 months before this paper was given. It turns out, we found out years later, that paper presented there was kind of off the subject in a way. Most of the other papers presented at that conference were on drainage theory, the theory and mathematics of flow of the water through the soil to the drain pipe, but this one was on equipment. The paper got the drainage industry's attention to the research progress of evaluating the corrugated plastic drain pipe and the plow end method of installation. We wanted a little larger, at least 3-inch diameter plastic drains for some additional research. There was no company in the United States that could find that was interested in even making molds and extruding the pipe for us for research purposes. Said there would never be any interest in that. And so we arranged with, and we knew we couldn't write a purchase order as being a government employee, government agency to Germany. So we contracted with the Armco Steel Corrugated Metal Pipe Division, who were interested in plastic pipes at the time, we gave them a purchase order. They in turn wrote a purchase order to Germany, had the molds made and the pipe made for us for research in the 3-inch diameter. We had pipes made in polyethylene, high density polyethylene, polypropylene, and PVC plastic, 3 different kinds. This one was polypropylene, white plastic. But they made the molds. Designs, corrugations were quite different than those tiny corrugations on the German pipe, and sent that off to Germany through Armco to get the pipe made. This was the high density polyethylene pipe. It had carbon black in it. That was a 300-foot coil, 3-inch pipe. By mid-1966, we began making special series of investigations and focus studies to determine the minimum strength requirements. In other words, we were satisfied that the corrugated pipe idea was going to be a way to go, but we really needed to know how strong did it need to be for long-term durability in the soil. And we wanted to develop early specifications and standards for the plastic drain pipe, and I was assigned to work some early with ASTM on developing some early standards. Dr. Schwab had put those drain pipes in Iowa State in the mid-60s. We encouraged him to go with us out there, and took our whole team and dug them up, and he helped us find the pipes he put in. They were polyethylene, 4-inch diameter, pulled into the mold drain, and that was in the early 1950s. And I think he finished his degree in like 54, 55. And he helped us find those. We brought samples back. We poured plastic mold into those and took out samples, but we put them in sandbox tests to see what kind of loads they would take. This was a compressed thing we put on. Norm was applying pressure, and I was watching it. We had instrumentation on it. I could show some of that. We also put a rig together so that it would be constant weight rather than just a screw, and so we could let it just sit there for a day or two to see the effect of time with a Ames dial type thing and indicator in the thing to measure deflection and to calculate the load based on the weight. Did some studies on the theory for rigid pipe versus flexible pipe under soil loading. For a surface applied load, for rigid pipe, the pressure it tends to concentrate on top of the rigid pipe, whereas on the flexible pipe it gives and the weight is picked up at the sides. So for the same depth in the surface load, the amount of load on top of the flexible pipe is less than it is on a rigid pipe. That wasn't understood by a lot of the people, especially the rigid pipe people, the clay people, wanted the flexible pipe that we were experimenting with to support the same vertical load as the rigid pipe. That's just not the case. The way the flexible pipe is put in trenches, in a trench is quite critical. A flat bottom trench allows it to deflect, where it was recommended to make either a 90-degree or 180-degree cradle for it to fit in to reduce the deflection. There was a lot of a theory developed in Iowa, Spangler, Dr. Spangler in particular, on the soil pressure around the flexible pipe as load occurred and soil settled on top of it. There was a revised Iowa formula because the original Spangler formula had an error in it, and Dr. Watkins, one of his students, found it, and they revised that formula. They called it the revised Iowa formula for the deflection, and it would basically predict the vertical or the horizontal deflection of the pipe under the soil loading condition. And we used miniature strain gauges on our sandbox and soil box to measure the soil pressure that was around the pipe. These are about a quarter of an inch diameter load cells, strain gauge load cells. Each of them cost about $500, and I remember at the time that the ARS fussed at me because I bought a device for $500 that's so small you couldn't even put a property tag on it, and so I told them that the engineering standards were more important than their accounting standards. About $500, and this was in the mid 1960s, so it was quite expensive for in that day for that kind of a thing. We used an Ames dial type of indicator for deflection inside the pipe as it was loaded. We also looked at the possibility of using a parallel plate, which the clay tile was loaded and broken between parallel plates as a part of their testing program. And so we looked at parallel plates as a deflection method and determined load and deflection resistance. And it was a time-dependent thing as far as we were concerned. and that's why they put a recorder on it to apply a load, leave it set, and watch the deflection over a period of time. The theory with the parallel plate load, we developed, looked in the literature that it was pretty well published. This is some of the sandbox tests with the actual samples from we dug up in Iowa, and it fit the theory pretty well. And then we looked at the stress in the wall, whether it's a smooth wall pipe or even corrugated wall pipe, in terms of the compression stress in the pipe wall, the bending stress if it's deflected, and the total. I developed the equations for the corrugation design, and the first corrugations were relatively simple, what I called square waves, so that made the analysis fairly simple. And this is, in effect, the kind of a corrugation I developed and sent to Germany to have the original pipe made. So we even tried to get it made so that the inside wall thickness and length and the outside wall thickness and length, the amount of plastic in both of those was equal, and therefore balanced each other, and the neutral axis of that cross section was right in the middle of the corrugation height. This is a fairly simple equation. Now later we developed the more complex equations where you had fillets in the corners and rounded roots in the corrugation, and the equations are much more difficult, but that's was used into corrugation. I've used those for many years now in designing corrugated shape for different sizes, particularly different size pipes. The parallel plate deflection resistance of the Iowa pipe dug up really showed us it was about 30 pounds of load per foot per 1/8 inch of deflection. And in terms of the ASTM pipe stiffness terms, that would have been about 20 pounds of parallel plate load per inch of pipe length per inch of deflection. And they called that the PII value. Today, that standard has increased a lot. Today, for a standard duty pipe, it's 35 pounds per inch length of pipe per inch of deflection, and for heavy duty pipe, it's 50 pounds per inch and when tested with parallel plate. Now, the parallel plate testing on this is with an N-Strom machine, which advances the two plates at a half an inch per minute, which I've always considered too fast because it's a time-dependent thing, but it was never able to get ASTM to modify that, and especially as it was less important as you got to larger and larger diameter pipe. When you got up to like 24-inch diameter pipe, a half an inch per minute wasn't that bad. But for a 4-inch diameter pipe, it was critical in my opinion, and never won that argument. The changes began to occur in the clay and the concrete drain tile products, and also in methods for handling and shipping tile to the job site. They were seeing the progress being made in the looking at plastic pipes, and particularly corrugated wall pipes. Some of the clay drain tile manufacturers made multiple pipe wall openings in the tile for soil water entry in response to the advantages reported for corrugated wall plastic drain pipe with many pipe wall openings, holes or slots along the pipe for soil water entry. Infield tile support and handling equipment was introduced, such as trailers, wagons, chariots, in response to ease of handling coils of the corrugated tube for the pipe. This was Hancock Brick and Tile, perforated clay tile. Bob Alpers, he was a vice president of sales, and this is a company, Hancock Brick and Tile, that became Hancor Incorporated. But these are pallets, and they used, I think they had six perforations for water entry per foot of tile. And that was to try to say that, yeah, their tile is just as good as the plastic. Has got a lot of holes in it. Other companies use the palletized tile on a chariot to transport it into the field. And this is a company, Hancock Brick and Tile, that became Hancor Incorporated. But these are pallets, and they used, I think they had six perforations for water entry per foot of tile. And that was to try to say that, yeah, their tile is just as good as the plastic. Has got a lot of holes in it. Other companies use the palletized tile Other ones use wagons and then chutes, pipe feeders. So this I'll indicate is a good example, and even the next one where you got pipe pre-strung. Uh, when they try to speed the thing up, you reach a limit where they're not going to get to 150 feet a minute with trenching it in, because that means that the crew has to manually handle 150 pieces of this pipe every minute to put it in a trench, and manual crews just can't keep up with that kind of a workload. And so the speed of installation with a trencher, regardless of how they mechanize it, it's not going to duplicate the 150 feet a minute or faster with a plowed in corrugated drain. At this point, when we started on the laser beam automatic depth and grade tool system for the drain plow, it was field tested in 1966 at Ohio State University. At this point, we'll stop this current webinar and cover the laser beam automatic depth and grade control system development, research, and testing in a following webinar.